going on, guys? It's Or Bust Season 1 Episode 12, the show where you design subwoofer enclosures, I 3D print them, and we throw them head to head to see whose is the loudest. Now, today's episode features an absolute unit of an enclosure. This is the Chungus. This is the Tuba HT, which is a horn loaded, a quarter wave design, so horn. And as the name suggests, the design was originally designed for home theater application, thus low frequencies. A lot of horns you'll find are designed for pro audio application. They tend to be tuned quite high, in the sort of high 30s, mid 40s for kick bass and highest efficiency with the minimal size. If you're lugging this stuff around with pro audio and gigging and stuff, you don't want it to be absolutely massive, and you don't always need the extension down to the sort of mid 20s like you would in home theater. So this design is based on much lower frequencies than some other commercially available horn designs that you might find. Now, when I say it's big, I mean it is freaking massive. This is the benchmark air-reported box, which performed really well considering it wasn't so great on the higher frequencies, but I think that's got more to do with the driver than the box. This was absolutely loud as hell on the lower frequency, the 25 scaled hertz. Now, if you look at these two boxes, you could fit 1, 2, 3, 4 of these benchmark air reports in the same volume that the Tuba HT takes up. Now, I think that the Tuba HT is going to be a really strong contender here in this series, might even top the leaderboard. However, you have to bear in mind, given its size, would it be able to outperform 4 of these? Well, I think probably not. So even though it might perform the best, it might not make the most sense if for a lot of people's real life applications. Given a certain amount of volume size that they've got available in their cabin, it might be better off to go with multiple smaller designs rather than one absolute massive beast that's loud but with a single driver. Now, the Tuba HT obviously is a horn design. It's very similar to the Fibonacci fourth and the half wicked one by means that the driver has a sealed chamber behind it and the cone then fires into the throat of the horn that expands outwards. However, the main difference is that with the Fibonacci fourth and with the half wicked one, the lower frequencies were mostly produced by the displacement from the cone only and directed by the horn mouth, but the actual quarter wave mode of the horns in those other two enclosures was really high, much higher frequency than really you'd be using here. Whereas with this enclosure, the quarter wave length here is tuned much lower, so we're actually going to get proper horn loading at the lower frequencies that we're testing. So I think that's one of the reasons it's going to perform so well. But of course, to see whether it's going to perform as well as we think, we need to test it. So the first thing we're going to do is drop it on the Dayton DATS V3 and see what the impedance curve looks like. I'm very interested to see this one. Ah yes, now this is the impedance sweep curve of a proper horn that is tuned low to the frequencies that we're going to be testing. Wow, look at this spiky boy. Okay, let's go through this together. We have the first impedance spike down here at 120 hertz. So that is basically the unload, where the driver is not loaded by the horn in any way, and we're not probably going to get too much output down there, just a bunch of excursion and harmonics, but that's okay because that is under the lowest frequency that we play. The lowest frequency we play is a 150. Now let's see where that is well on the way to the first impedance dip here. It's almost right at it. We're down at 5 ohms. So that low frequency there is going to be well loaded, very well loaded by the horn. The actual impedance dip itself reaches its extremes at 167 hertz. So that's where the driver would be held stillest by the horn. Now, the way that any quarter wave resonator works is that as you go up the frequency range, the line or the horn will hold on to the cone at one frequency, then let go, and then hold on at the next resonant frequency up the line, and then let go and hold on again. So that's where we're seeing these spikes and dips going gradually upwards. You got the horn grabbing on and loading the cone, letting go, grabbing on, letting go. So this first impedance null here, this impedance dip, is the first fundamental, the first frequency that this horn is going to be resonating at and unloading that driver. So the next frequency we play is a 198. Now we've got a very steep climb here to a monstrous impedance spike. It is huge, very steep, and our 198 is just a little under halfway up this next impedance spike. We've got 6.7 ohms, so we're still going to get some reasonable loading on the cone there, but it is on the way up to an impedance spike. Now, when I did some testing on this with a perspex top, just so I could check the excursion, at this frequency, which is 33 hertz scaled, there was a bunch of cone displacement, like enough that I couldn't actually reach the 15 watts that is our power limit here. So I hate to think how bad it would have been up at where this this next impedance spike is, which is at a high 222 Hertz. I think playing that frequency, the cone will just want to rip itself apart on about 2 watts. Now the next frequency up we play is a 270, which is 45 scaled Hertz, and that is on the way down to the next impedance dip. We are at 5.5 ohms, so again we're going to be loaded fairly well down there, but not making full use of the horn load at that specific frequency. The next dip is actually at 325 Hertz, which is somewhere in between the last 2 frequencies we test, 270 and 360. So this second impedance dip signifies the second harmonic, the second fundamental frequency that this horn is going to load the cone at. And our last frequency, like I say, is 360 Hertz, which is just after the impedance dip here. So we're going to be loaded well at both those 2 last frequencies, which I think is a good thing, because I think this is going to be relatively flat across the board. We're quite well loaded at the 2 top frequencies and the lowest frequency, with the only one with a bit of unloading being the 33 in the middle. The next impedance peak, the third impedance peak, where the horn just lets go of the driver, is at 400 Hertz, which is above what we will be testing at anyway, so we don't have to worry too much about that. But you can see on the graph here how this kind of pattern of loading, unloading, loading, unloading continues all the way up. We've got 401, like I say, as our next peak. Then the next dip we've got down here at about 550 Hertz. And then a little peak here again at 630 Hertz, and a dip in between at 741. So you can see it going up the range there. And the reason that these impedance peaks get smaller as it goes up is just because the driver itself, when it's unloaded, is presenting less impedance rise as the frequency gets higher. Impedance rise is as a result of the coil moving in the magnet. So if you've got less excursion, you're going to get less impedance rise anyway. So you're going to get more excursion at the lower frequencies, hence the massive peaks down low, and then less as you go up. That's interesting stuff, but what does she sound like here, open on the table? Let's get a quick listen. We're going to play 25 scaled Hertz first, which is 150. And usually with a lot of other boxes, you tend to get a lot of chuffing down here, especially with ported boxes, just because of the amount of air being shoved out of a port or whatever the case may be at this lower frequency. But this is such a large mouth. I can feel the force of the displacement, like my hand being pulled in and out here. This is very strong, but there's no chuffing or really much harmonics that I'm picking up compared to other boxes, just due to the size of this mouth. I would say, based on my ear, that's got to be one of the cleanest 25 scaled Hertz that we have heard, or I've heard so far from any of these boxes. Really nice. Way cleaner than the Fibonacci 4th and the Half Wicked one, because this line, this horn is actually loading the driver down there. So we're not listening to just the cone displacement, which can introduce harmonics as it moves. We're listening to the horn. So this next one, 33 scaled Hertz, a 198, is on its way up to an impedance peak. So let's have a listen. We're going to be listening to more of the cone here than the horn. That's still mega loud, and actually not as harmonic as I thought it might be off the driver here, even though we're listening to a lot of the cone. Now I can tell that we're listening to the cone here because as I increase the volume to a certain point, you can hear harmonics get introduced as the woofer surpasses X max. It stops becoming linear and you can really hear the distortions come in. And also I can see on the watt meter here, which you can't see right now, but it's so efficient. That wasn't registering any watts, it just said 0 on the screen there, and that shows me that the cone is just proper going crazy and it's super efficient at that frequency. I suspect that the air spring in that sealed chamber might actually be aiding this specific frequency, which is on and unload. Now that might be able to be calibrated better if with a different volume of sealed chamber, so that the air spring inside aids one of the frequencies that the horn is actually loading the cone at, rather than one where the horn has let go of the driver and the air spring is further aiding its movement. That could be calibrated a little better, I think. Let's try the next one up. 45 scaled Hertz, a 270. Again, sounds clean. Doesn't really sound harmonic, nothing weird going on, lots of displacement. Oh, that is loud! That is a very potent 360, bloody hell. And it sounds clean too. Yeah, not really much harmonics going on there. Let's just check that that's actually what we're hearing. Let's just have a look at the waveforms on Room EQ Wizard to see if it's actually as clean as it sounds. So our 25 starts out looking pretty clean and only distorts badly once we really start pushing the driver. Yeah, we don't have the best symmetry between the top and bottom of the sine wave, but it's honestly not that bad. And on the RTA, yeah, there's some harmonics there, but they're nowhere near as prominent as we've seen on previous enclosures, and definitely nowhere near to overtaking the fundamental as we've actually seen before. Next up, our 198 Hz starts starts off looking pretty clean again, gets a little spiky towards its limits, not as bad as the 150, and the sine wave looks a bit more symmetrical than the 150. On the RTA, the fundamental spike stays on its own for longer, only as we approach the limits do the other harmonics creep in really quickly, and actually the third harmonic overtakes the second, which I don't think I've seen before. Next up is 270 Hz, and this is interesting because the waveform looks relatively clean, but it's lent back, it's kind of slanted backwards, and I've noticed that's because at higher frequencies this driver likes to oscillate on an outwards kind of center point. It kind of pushes itself outwards and stays there and oscillates around a new center point. I think that's just something to do with the driver. And the second harmonic doesn't come up straight away, only as we get towards limits, and the others aren't too prominent either. Now our last frequency, the 360, this sounded very loud in person. This sine wave looks beautiful. Even up very loud, it doesn't really have many visible deformations. It's nice. And this comes across on the RTA graph as well. We have a huge fundamental spike before even the second one appears. Only right at limits do we get a tiny baby second and third harmonic. Yeah, super interesting stuff, and it does look promising, but I'm sure you want to see how this sounds as much as I do. So let's get this in the test chamber, and as far as positioning goes, I think we're probably going to be best having this firing backwards and with the horn exit on the same side as the sensor. Seems to be loudest on most other enclosures, but I will test both, and whichever is loudest will be the one I go with. So let's get it in there and run some demo tracks and see how loud it is. Headphone users, you've been warned. Okay then, now I don't know about you, but that looked freaking loud. It was moving the piece of fabric in the open doorway at more frequencies than any other box that I think I've seen so far. It was consistently rattling it like loads, moving it a lot, whereas other boxes have only really done that at like tuning frequency or one specific frequency, whereas this was across the board, seemed very loud. So I'm super interested to see what it does on the meter. Let's start off with open doorway, as always, 25 scaled hertz being at 150. This should be pretty loud because it's just right on the horn loading frequency, and it is the cabin Helmholtz mode as well. 15 watts has been calibrated on the watt meter. Let's hit it and see what it does. Bloody hell, a 146.7, ladies and gentlemen. That is the loudest score we've ever seen so far on Boom or Bust, surpassing the half wicked one and the Fibonacci fourth and my benchmark error report. Like everything in the room is like vibrating, is crazy, and that is only with 15 watts calibrated on the watt meter here. Wow. So yes, it's loud. It's not monstrously louder, like it's not 4 dBs louder than the other enclosures, but it definitely is a step above. Now the interesting point will be whether this can maintain those high dBs at the higher frequencies. So let's do the 33 scaled hertz next, which is a 198. Now when I tested this out on the bench, I wasn't originally planning to go all the way up to 15 watts because the driver started reaching mechanical limits even with only about 5 watts. But since we put it in the cabin here, there's enough cabin loading that it seems, by my ear anyway, to be loading the cone enough to get us up to about the 15 watt mark. So I'm just going to extend it, go for 15 watts, and if the driver rips itself apart, then so be it. So let's see, can it maintain? Whoa. Not only did it maintain, it's louder. That's not even the cabin. Actually, well, it probably might actually be the cabin Helmholtz. I was going to say, empty, this cabin has a Helmholtz mode of about 160-ish, 140, 160-ish hertz. But we've added a great big block of plastic here that's taking up some volume, therefore raising the Helmholtz mode. So the Helmholtz mode is probably a bit higher than it would otherwise be. Oh! Can't believe it. That's mad. Now, surely it can't keep this up with the higher frequencies. Let's do 45 scaled hertz next. This is the one where the sine wave is a bit slanty. I don't know if that's going to affect the score at all, but let's see. Okay, yeah, so it's still quite loud, but it is well outside of both the quarter wave mode and the Helmholtz mode of this cabin now, and also not the most efficient frequency that this horn wants to play anyway, a 135.2, still really impressive. Now lastly, 60 scaled, which is a 360. I think this actually might be a bit louder again than the 45, just because of how loud it sounds open on the bench here. Let's have a listen. Oh, it's potent. Wow, 138.6. That is that not the loudest we've ever seen at 60 scaled? Whew. Now let's put the cabin door on and test again with the cabin closed off. I wonder whether the door's actually going to stay on. It's going to get blown off. The cabin has been sealed off. Whether it will stay there is anyone's guess. So 25 scaled, let's just roll it up and see how loud we get. Already a 132. Bloody hell, not even got to 3 watts yet. Okay, 15.5 and a 138 dead. That is mad. That is louder than some of the enclosures we've seen with the door open. 33 scaled. 15 watts and... Oh my god. That is almost a 140 with the door closed. 45 scaled. 15 watts and a 130.1 and 60 scaled. 15.8, a little high, but a 128.1. Okay. Interesting how that was less than the previous frequency of the door closed, but it was greater with the door open. Must have been some kind of resonancy stuff going on there. So that means not only have we surpassed our 140 dB average, we have smashed straight through it with a 141.83 dB average with the door open, putting this solidly into first place, way above any of the others. With the door closed, however, we reach a 133.93. Not quite first place, actually third place. And sadly, we have to say goodbye to the Derek V5 on the door open side and the Paul ABC on the door closed side. Now, first thing I want to address is why was the door closed score not first place? And why was the half wicked one in Fibonacci 4th seemingly louder than the Tuba HT with the door closed, given that this was so much louder than all of the others with the door open? I believe it's got possibly something to do with my testing methodology. So the door open test is definitely the most consistent one, the one that you can rely on. The door closed one, when I was building this test cabin, I was in a bit of a rush to get it finished, and at the last minute, the last thing I had to do was to create the door to go on the side, and to be honest, it's just pushed up against the cabin with blue tack, and obviously there's a hole for the sensor wire to come out of. Now, I think it's pretty consistent between tests, but I can't be sure. There might be some times where I've pushed it on a bit harder or a bit less, or there might be more of a gap around the wire or more of a gap around the edges or something like that causes the door closed test to be a little bit inconsistent between boxes. So the most reliable test with these boxes is always going to be with the cabin door open. And the door closed, I wasn't even really going to include it, but I thought that some people would want to see that test done because it kind of follows the old school DB drag rules with the cabin all sealed up. So naturally, I always try to make a consistent seal with the door, but it could be the one that has the least consistency. I would always go by the door open when comparing these boxes. Secondly, there's also a thing where this enclosure leans on the lower frequency horn loading to get those ridiculous scores down at those lower frequencies. Now with the door sealed off, we lose the Helmholtz mode of this cabin, therefore relying on only the quarter wave mode of the cabin and also just the performance of the driver and box itself. Now, given these other two enclosures, which are ahead of the Tuba HT with the door closed, use just the seal chamber mostly to produce those lower frequencies, and the horns are shorter, therefore will probably help out on the higher frequencies more so than the Tuba HT. That may also have something to do with why they are louder with the door closed, but I'm not entirely sure. One thing we could do at the end of this season is to retest the top 5 enclosures, but with a much more consistent door seal method, just to confirm whether there's actually any differences in the box design being louder with the door open versus closed, or whether it was just variance in the testing. Now obviously that's insane. This is loud as heck, but remember, it's also bloody massive. It is super heavy. It used a whole reel of PLA. It's like a kilogram in weight, and that is going to scale up as well. If you wanted to build one of these for your car, it's going to be a freaking monster. It's going to be super heavy and massive, and I'm not super convinced that you would be louder with this horn and 112 than if you used the same amount of wood and the same volume space to build a box for 412s, for example. So, and that's something we may visit at the end of this season. We'll take the winning enclosure and look at its volume and see, right, what happens if we squeeze more drivers into that same volume? Is it then louder than the winning enclosure from season 1? In that case, for the Tuba HT, assuming that this wins season 1, we would probably do a box for 412s like that with a big ass port and the firing over the back and see what that does, and I suspect that would probably be louder than this. And that leans into another interesting scoring method we could do for this season. At the end, once we've got all the results, we'll take every single enclosure that we've tested, even the ones in bus status, and we'll do a score for performance versus size. So I'll work out some kind of formula to see the overall performance, dB average across the range of frequencies against its size, and the winner of that category would have the loudest score relative to its size. So that would be another really interesting way to do it, because okay, yeah, let's say this is definitely the loudest, but let's say, for example, this wasn't that far off. So having 4 of these in this same volume size would clearly be louder. Therefore, is this the best enclosure to build? Probably not. You're probably better off building one of the smaller ones and just having more of them, for example. So although this series is all about what's the loudest enclosure for a specific driver on a specific amount of power, in reality, the most important factor might not actually just be how loud it can get, but also how big is it? How loud is it for its size? That might be the most important factor that I kind of hadn't really thought about. But anyway, that could be something I can research and look into for another season. But until then, if you think that you have the design to dethrone the Tuba HT, from the door open side at least, then feel free to send in a submission. There is a video in the description that details all of the parameters you'll need to design an enclosure for this series and how to send it in. And if you're interested in sponsoring this series in any way by having a sticker on the test cabin, a sponsored message or segment in one of these episodes, then there's an email description and there's an email address in the description as well. So guys, hope you enjoyed this one. I will see you in the next one, and I'm very excited. Got some crazy enclosures coming up, so see you then.